So, hello everyone. Thanks for the introduction, Robin. I'm Sharat, a final year PhD student from University at Buffalo. So let me get started. So today I'll introduce you to our system, which improves data management on mobile systems by making it more customizable. We call our system BlueMountain. You'll know why we would need that when we closely see the state of mobile apps today. So there's an explosion of apps, and nearly anything you can think of, there's an app for that. These apps are not just growing in numbers, but they're also getting increasingly sophisticated, especially if you take a look at the way data is managed. A modern app uses all forms of data and all forms of storage, including cloud, local storage, and all of users' devices. They use complex and rich data-centric interactions with elaborate policies to manage user and app data. In this ecosystem, a developer builds an app and distributes it through an online app store. A user sees a list of published apps that he wants to install and picks whatever he likes. From a developer's viewpoint, in this process of building an app, it's not only have to create the app logic, but also has to spend significant time in crafting the data management logic, which includes policies and mechanisms for managing data. This effort is often orthogonal to the core application logic and repetitive across apps. To further understand this complexity, let's see what a developer has to go through when he builds an app. To start with, a developer has to decide where the data has to be stored from a pool of storage, including local storage and various cloud providers. Secondly, he has to consider a lot of policies which could be critical for the app. For instance, some app might want to upload the data instantaneously, while other apps might want to optimize for local storage or energy or bandwidth. Overall, this model is hard for developers. After going through this exercise of tuning the data management, a developer would end up with an app as illustrated in this example, in which the data management logic is tightly coupled with the app logic. This means once a decision is made on data management policies, which are made during the development time, it's hard to make any changes. Overall, this model makes the development of apps harder and potentially slows down the innovation in the space of data management. The other side of the story are the users. When a user is using an app, they're often constrained by the developer's decisions. For instance, when using an app, if an app is uploading data to Dropbox, a user might have totally different requirements in mind. Moreover, different users might have different requirements. Illustrating this with an example of a photo editor, we can see how users might have differing preferences. With these distinctive needs, it's hard to come up with a data management solution that satisfies everyone. So what do we need to solve this problem? So ideally, what we need is a solution in which a user can pick whatever the solution that best fits their needs, which would in turn free up the developer's burden of making the data management decisions on behalf of users. Additionally, if they restrict the solution to the user space only, we can also make the solution easily deployable. Now that I've described the problem and also mentioned the requirements for the solution, let me introduce you to our system BlueMountain, which achieves all this by decoupling the data management logic from the app logic. We propose a new ecosystem in which, apart from the regular apps, we have what we call as the data management apps. These apps are exactly like regular apps and distributed through the online Play Store, but they implement data management policies and mechanisms and are meant to work in conjunction with the regular app and manage data on their behalf. In this ecosystem, a regular app implements app logic only, assuming a locally available storage. A user in this ecosystem can install both the applications and link any regular app with a data management app of their choice. Let's see this ecosystem in action. In our ecosystem, there are two kinds of developers. Firstly, there's a regular developer called Bob, and Bob develops a photo editing app. So while developing, Bob just concentrates on the app logic for a locally available storage for photos. There's another kind of developer in the ecosystem, Ted, who develops data management apps. So Ted develops a personal cloud app, and when developing this, he considers only how to manage data across the user's cloud. So a user in our ecosystem can install the photo editor alongside the personal cloud, and our framework facilitates the personal cloud to be combined with the photo editor app. So what a user has is a photo editor app that manages data on her personal cloud. Now that we have seen the ecosystem working, let me explain how we can design a system like this. For that, we need to answer two questions. First, we need to have a way for developers to build the data management apps. And second, we need to address how a data management app can be used with a regular app. Let's consider the first question of building a data management app. Our prototype implementation on Android, our prototype implementation is on Android, and a data management app can be built by using the Android's SDK. But we still need a well-defined interface to achieve this. A naive approach to this would be to have a data management app use the Android's default storage interface. When such an implementation is used with a regular app, we can achieve the desired data management functionality. For instance, the default implementation of file input stream reads a local file. If a data management app wants to change it to read a file from the cloud, they can do so, and it can change the behavior of reading a file. Well, this approach is relatively straightforward. It's very messy. So Android, as we know, has a broad and complex set of APIs. When we try to enumerate all possibilities of accessing storage on Android, the list is large, and it runs through hundreds of methods across tens of classes. Creating a data management app that implements each of these methods is hard. To simplify this process, we need to analyze the APIs further. For instance, both file input stream read and file reader results in a file read. So by changing the way a file is read, we can change the behavior of both these classes, file input stream and file reader. With most such analysis, we can reduce a large number of Android storage APIs into a smaller set of APIs, which we call the BlueMountain APIs. In this reduction, we handle three cases: for files, key value stores, and databases using different strategies. For simplicity, to handle files, the BlueMountain APIs uses object in place of streaming I/O. For key value store, it has access through the shared preferences API, which uses a backing XML file. So to handle the key value store, and BlueMountain API just treats it like a special file. To handle databases, which are a little more complex, we reduce a large set of app-facing database APIs to a simple SQL statement which could be executed over update and query. Some cases are more complex than this, as we have to see the trade-off between simplicity and functionality. We provide details in our paper. In summary, by implementing this simple and new interface which we are providing, anybody can build a data management app. That brings us to the second question. How do we make a regular app use the data management app of user's choice? The first problem here is the mismatch of the APIs. While the regular app developers use Android storage APIs, the data management app developers use the BlueMountain APIs that I just described. So we have to bridge this gap. To do that, we created a translation layer which seamlessly converts the Android storage APIs into BlueMountain APIs. We then take this translation layer and inject it into a regular app using bytecode instrumentation using a tool called Raptor, which is an API virtualization tool which our research group had built earlier. After this, our translation layer will correctly intercept all Android APIs and convert them to all Android storage APIs and convert it into BlueMountain APIs. Now, a regular app is ready to execute BlueMountain APIs. But in order to do so, we need a way for classes in data management app to be invoked by a regular app. To do that, we have built a dynamic loading module, which is also injected with the translation layer. This uses the Android's class loader and loads the classes from the data management app into the regular app. Our predefined interface allows us to freely use reflection from this point without the typical overhead that reflection is known for. At this point, the regular app can delegate all of its storage calls through the API, through the module we just loaded, which can freely access both the local storage as well as any external APIs. Lastly, the data management app might want to pass any runtime configurations to the regular app, such as changing the preferred time of upload. This can be done through the intent service module, which also gets injected. Thus, we combine the translation layer, the dynamic loader, and the intent service and call it the BlueMountain framework. Thus, anybody, even without having the source code of an app, can feed the app to a transformer, which injects the framework and converts a regular app into a BlueMountain-enabled app, which is now ready to take advantage of our system. This concludes the architecture of our system. Lastly, I want to discuss the performance of our system and all the components we have built. We evaluate our system on 3 different parameters. First, we evaluate it by building several use cases to evaluate the practicality, usefulness, and flexibility of our system. Second, we measure the overhead due to our framework. And third, we evaluate the correctness and the performance of our transformer. Our goal with the use case implementation is to show that sophisticated data management solutions can be implemented even with a simple interface such as ours. To this end, we implement two systems for managing files based on previously developed research systems that we liked. The first is a personal device syncing system based on PS Cloud, which uses dynamic file placement to sync files across all of users' devices. Our data management app syncs files across mobile, cloud, and desktop, depending on the network's availability. The second system is an efficient cloud syncing system for syncing file to cloud, which proposes various techniques for efficient file syncing. So our data management app implements a variable chunk syncing to Dropbox. To completely re-implement these systems was orthogonal to our goals. So what we wanted to show here was it's possible to implement these complex systems. Our framework provides the flexibility to do so. Next, we evaluate our system for database management. We could not find any research systems that manage mobile databases, so we came up with 3 intuitive solutions to sync databases to cloud. First system treats the database as a file, divides it into multiple chunks, and uses a technique similar to rsync to upload it to cloud. The second system records all the SQL statements in an operation log and replays it on the cloud. The third system breaks the databases into multiple databases, each having a single table, and uploads each of these databases independently to cloud. Thus, by these 5 systems, we have shown the flexibility of our system. Next, in order to understand the overhead of our framework, we use micro benchmarks. We have created a benchmarking app which can measure the time taken for various file and database operations. Our baseline is the results of directly calling the Android Storage API, which we call as the native performance. We measure the overhead of our framework by allowing the storage calls to pass through our translation layer, but instead of routing the calls to the loaded data management app, we make the I/O calls directly from the framework. We call this the framework overhead. Lastly, we use a basic data management app which uses a local-only storage and route all the storage calls through it. This overhead also includes the overhead due to dynamic loading and reflection. We call this the data management app overhead. To see the results, the graph here shows the performance of random read at 4K chunks for various file sizes measured as IOPS. The blue bars indicate the native performance, and the green bars indicate the framework performance, and the red bars indicates the data management performance. The performance of data management and the framework is identical. This tells us the overhead due to reflection and dynamic loading is negligible, and most of the overhead comes from the translation layer. When we repeat this experiment across random and sequential I/O for various file sizes as well as database operations, we see that our framework incurs only modest overhead. The full evaluation is present in our paper. Lastly, we evaluate our transformer. To evaluate the correctness, we use multiple strategies. First, we downloaded 5 apps and instrumented them, and we test them manually to ensure that there is no loss of functionality. After we passed this test, we downloaded 400 more apps and ran it through the Android UI automator. We ran the original as well as the instrumented app, and monitored all the call logs, the new exceptions, and crashes. After we ensured that it behaves as expected, we consider our framework, our transformer to have correctly instrumented the code. We also measured the increase in parameters such as energy, heap size, and code size, and we present this in greater detail in our paper. Before I conclude, I want to discuss some of the challenges and open questions about our system. The first is the concern on security when using BlueMountain. In particular, a malicious app can pretend to be a data management app and compromise a user data. While this is a valid concern, it can be solved by using many of the existing techniques. Since the data management app is also distributed like regular apps, we can potentially address the solution by using techniques like Google Play Protect or information flow analysis. The second discussion is the coverage of our APIs. While our reduced set of APIs is sufficient to handle most of the cases, we still have to extend our interface to handle advanced cases, such as custom cursor factory in case of databases or accessing low-level files through file channel and file descriptor for files. Lastly, I would like to conclude by summarizing our system. So we have built BlueMountain to decouple data management logic from app logic. This makes the development of apps easier, provides more flexibility to users, makes it possible to deploy novel data management solutions, and all of this works on an unmodified platform, requires no developer intervention to support legacy apps which are using local storage. Thank you.